Wouldn't it be stellar if you could walk through walls? Or maybe teleport to Florida for spring break? Well, thanks to quantum tunneling, theoretically, this is possible, but there's a catch. While this is possible, there's an infinitesimally small chance of you even being able to walk through a thin sheet of atoms unhampered or unaffected. So how does quantum tunneling allow for this to occur? Well, for starters, quantum tunneling can only be explained when we define a particle as a wave. In 1924, Louis de Broglie discovered that all matter has wave properties. He described particles as matter waves, each particle having its own wave packet describing its probable position. The wavelength of this wave packet is found using de Broglie's famous equation, lambda equals Planck's constant over momentum. When a particle's matter wave had a large wavelength, the particle had a very uncertain position. In contrast, when the wavelength is small, the position is more certain. When a particle comes in contact with a barrier, its wave function doesn't just stop. While some is reflected, part of the wave actually enters and travels through the barrier, though it decreases exponentially while inside. Though the amplitude of the wave function is very minuscule in size after it leaves the barrier, it doesn't ever reach zero. This makes it possible for the wave to reshape itself on the other side of the barrier, therefore tunneling. Physicists have figured out that the probability of a particle tunneling is actually predictable using these three equations. T plus r equals 1, t equals e to the negative 2 times length times alpha, and alpha equals rad 2m times u naught minus e all over h bar. To make sense of this gibberish, the t is the transmission coefficient. This represents the fraction of particles that tunnel through a given barrier. The r stands for the reflection coefficient, the fraction of particles reflected. The L is the length of the barrier, and U naught is the height of the barrier expressed in terms of potential energy. The M is the mass of the particle, and E is the energy of the particle. For those who are unfamiliar with h bar, it is the Planck's constant, h, divided by 2 pi. These equations weren't the only thing that scientists discovered about quantum tunneling. Physicists desperately wanted to figure out if tunneling could be the long-awaited answer to traveling faster than the speed of light. To test this, physicists set up an experiment where 2 photons would be fired and would both arrive at their own detector, both traveling the same distance. The only difference was a barrier was placed in the path of one of the photons. The results were astonishing. Just as it was hypothesized, the photon that tunneled through the barrier arrived at the detector slightly earlier than the other photon. So that's it, right? Quantum tunneling is faster than light. Well, not so fast. Even without the barrier, there is still an uncertainty in position. A photon doesn't require a barrier to tunnel. All the barrier really does is filter out the photons that don't reshape their wave function to be in the space beyond the barrier. Theoretically, the photon without the barrier in its path could still arrive before the tunneling photon, as its uncertainty in position includes it. But how can uncertainty of position be calculated? Well, using the famous Heisenberg uncertainty principle, we know the uncertainty in position is a calculable value. The principle states that position and momentum cannot be known with 100% precision at the same instance in time. It states that the uncertainty of momentum and uncertainty of position are correlated, and it shows that in its well-known equation, uncertainty of momentum multiplied by uncertainty in position is greater than or equal to h over 4 pi. So does this uncertainty in position lead to an increase in the speed of light? Well, yes, it is an increase, but only within the limits of the Heisenberg uncertainty. Another big question was, can we observe this tunneling effect? Could we watch it? Well, sadly, if you were to observe the particle, it would collapse its wave function and behave only like a particle. Therefore, the particle would be unable to tunnel at all. This is an example of the quantum Zeno effect, which states that an unstable particle, if observed continuously, won't ever show signs of being unstable. In observing a particle, you essentially freeze its evolution. One great example of quantum tunneling being affected by the quantum Zeno effect was an experiment run by 3 graduate students at Cornell. Arla Schaefer, Yogesh Patel, and Harry Chung cooled a vacuum chamber to only a billionth of a degree above absolute zero and suspended around a billion rubidium atoms between two laser beams. The atoms were arranged in a lattice-like form, just as they would in a crystalline solid. At such low temperatures, the atoms should be able to quantum tunnel anywhere in the lattice. This is because in these low temperatures, the velocity of these atoms is very close to zero, meaning there is a lot of uncertainty in position. In the experiment, the researchers showed that they were able to suppress quantum tunneling just by watching the atoms. Crazy, right? So, quantum tunneling shows us that particles can travel through barriers that it normally could not. It allows instantaneous motion, but it has its restrictions, which is defined by the uncertainty of position in the Heisenberg uncertainty principle. Lastly, quantum tunneling allows to appear a violation of causality, which is the principle stating that everything has a cause. However, physicists continue to question if tunneling can be triggered by some unknown quantum effect in our universe, or if tunneling just occurs without cause. Thanks for watching. If you enjoyed, make sure you give that like button a good ol' smack. And until next time, I bid you farewell.